Welcome back to the matrix. Today we will be plumbing the depths of matrices and learning how to use matrices in solving systems of equations. In this lesson we will be covering a lot of material. I highly encourage that you use the pause and rewind buttons for sections that you need to take a little bit more slowly or need to see over again. These identity matrices are basically filled with just ones and zeros. The ones are along the diagonal from the upper left hand corner to the bottom right hand corner, and everything else is filled in with 0. So what the identity matrix does for us is basically, if we were to multiply a matrix, any matrix we can call A, times the identity matrix, we end up with the original matrix A. So in other words, it's just like multiplying by the number 1 when dealing with real numbers, except this is the matrix version of that. And conversely, we can multiply I with A and still get A. But don't take my word for it. Let's actually take a look at this and see how it works. We will be multiplying a 2 by 2 with a 2 by 2. Now hopefully you will are starting to be able to multiply matrices without the assistance of the slips of paper. By the time we get around to the test, we won't be using those. So let's go ahead and try this without the use of any aids. So we'll start off by multiplying 3 and 1, which will give us 3. Then 2 and 0, which will give us 0. 5 and 1 will give us 5 plus 4 times 0. Next we'll do 3 times 0, and then 2 times 1, 5 times 0, and 4 times 1. We simplify what we have, and that's going to be 3, 5, 2, and 4. And that's the original matrix we started off with. So we can see that the identity matrix actually does what it says it's supposed to do. Okay, now the next thing I want to talk about is inverse matrices. So let's say matrix A and matrix B are inverses of each other. If we multiply them together, you end up getting the identity matrix. That's what makes them inverses. So if I say A times B, that's going to give me the inverse matrix. And likewise, B times A would also give me the inverse matrix. We denote the inverse matrix as the matrix variable to the negative first power. That's how we generally indicate inverses, is to the power of -1. So let's try this out. So I have two matrices, a matrix A and a matrix A and a matrix B. We'll call the first one matrix A. So this is A and this one's B. So hopefully if we do this right, we will get matrix I. So let's start off. 3 times -5 gives us -15, and 8 times 2 is 16. 2 times -5, -10, and 5 times 2 is +10. Next, 3 times 8, which gives us 24. And 8 times -3 gives us -24. Then we're going to do 8 times, let's see where we go. Now we're going to do 2 times 8, which is 16, and 5 times 3, which is negative 15. Alright, so let's see what happens. So this gives us 1, and then 0, and 0, and 1. And lo and behold, we have the identity matrix. So A and B are definitely inverses of each other. Okay, so since we know what an inverse matrix is, how do we find it? Well, let's say we have a matrix A, B, C, D. We can find the inverse of A to the negative 1, as 1 over the determinant of A times, and then we take our original matrix and D and A, well, A and D will flip places along the diagonal, and then the C and B we will make negative. So we modify the original matrix and we multiply that with 1 over the determinant. So recall that the determinant is AD minus CB, and then when we get that 1 over determinant, that's going to become a scalar. Our scalar, in fact, that we multiply with our modified matrix, thus giving us our inverse matrix. So let's give this a try. Okay, so let's say I want to find the inverse of this matrix A. 5 times negative 2 and 8 negative 3. Not times, but it's a matrix. Okay, so the inverse of A is found by 1 over the determinant of A. So that's going to be 5 times negative 3. So it's going to be negative 15 minus 8 times negative 2, which will give us negative 16, which turns into positive 16. We're going to multiply with our modified matrix, so we're flipping A and D, so negative 3 here, 5 there, and changing the signs here. This becomes negative 8, and B becomes positive 2. Okay, let's go ahead and simplify this. This becomes 1 over 1, so just 1, and negative 3, 2, negative 8, and 5. And lo and behold, we have our inverse matrix. So inverse of A is in fact, so the scalar is 1, so that's going to make it real easy for us. 8 and 5. So depending on what your scalar is, it can become really easy to use, or it could be a little bit more of a challenge. It just depends. Sometimes you get weird fractions, sometimes you get whole numbers. In this case, this first one, it was really nice. Okay, so we know what an inverse matrix is. Why would we want to use it? Well, let's say I want to solve for a matrix X. Okay, well, I have this equation of matrices, matrix A times matrix X equals matrix B. So kind of like if we were to say, some number times X equals another number. But we're just doing matrices. How do we solve for matrix X? Well, it works the same way with matrices, in a sense, as we do with deal with real numbers. We want to isolate our variable. And in this case, we want to isolate our variable matrix. So how do we do that? Well, normally you'd think, well, I'm going to divide by A on both sides, and then I got it. But we're not doing any matrix division. So what do? Well, we got to get rid of the A. And to do that, we're going to multiply by the inverse of A. So the idea is this. Here's matrix A, here's matrix X, and here's matrix B. So we want to multiply both sides by the inverse of A. The inverse of A. Okay, remember what you do to one side, you do to the other. Well, matrix A and the inverse of A, as we just learned, gives us the identity matrix, I. So we'd be left with identity matrix times the variable matrix X, and then B, and then times, and then, well, actually, I made a mistake here. You have to be careful. You have to be careful about how you multiply your matrices together, because it's not commutative. So really, I can't put my inverse in the back. I have to put my inverse in the front. So in fact, it's going to be the inverse of A times matrix B. Otherwise, you're not going to get the correct solution. So here we are, the inverse of A times B. Well, then the identity matrix times any matrix gives us that. So we're left with the variable matrix is in fact equal to the inverse of A times B. So with that concept in mind and how this works, it becomes very easy for us, in a sense, to solve this. But the first thing we have to do is find our inverse of A. So this is matrix A in front of the X. So the inverse of A is equal to 1 over the determinant. So that'll be 15 minus, so negative 7 and negative 2 gives us 14. Then our modified matrix, so we swap A and D, so 5 goes here and 3 goes here, and then we change the signs on B and C, so positive 7 and positive 2. Okay, so this is going to become 1, so 1 times this matrix is just going to leave us with 5, 2, 7, 3. Okay, so this is our our inverse matrix. And so we would multiply this matrix on either side here. So it would look like 5, 2, 7, 3 times 3, negative 2, negative 7, 5 times matrix X is equal to, okay, so the inverse first, 5, 2, 7, 3 times negative 2, 4, 3, and negative 1. So when we multiply, now we multiply the inverse of A with A, which will give us the identity matrix 1, 0, 0, 1 times matrix X. Then we multiply inverse of A with matrix B. So let's see, that's going to give me negative 10 plus 6, then negative 14 plus 9, 20 minus 2, and 28 minus 3. So the identity matrix times matrix X is equal to negative 4, this is negative 5, and then 18 and 25. and we just solve for x. Now you can check your work by multiplying matrix A with matrix X and see if you get matrix B. So there is a way to check your work with these. Okay, so let's put all of this together and everything that we've been learning about matrices, and it all comes to this: being able to solve a system of equations with matrices. Here's how we do that. So we're going to write our equation in the same form as our last problem. We have matrix A times matrix X gives us matrix B. However, we're actually going to put variables into matrix X. And matrix A is going to contain all the coefficients of X and Y. And then matrix B is going to contain all our constants. So let's take a look at this. When we have it set up, then we're going to go ahead and solve it just like that last problem. We want to make sure that both our equations are in standard form before we begin. And so here we have negative 2x plus 3y is equal to negative 11, and 5x plus y is equal to 19. We'll set up our matrix by, let me get a eraser. We'll set up matrix A with the coefficients. So we'll start with the first one, which is negative 2, and then 3 on the y. Then the second equation we'll put on the second row, 5 and 1. Now matrix X will actually put the variables X and then Y, which will then give us, we'll put in our constants of negative 11 and positive 19. Cool, there we have it. Now that we have our equation of matrices, we will find our determinant of A and the subsequent inverse. So 1 over the determinant is negative 2 minus 15 multiplied by our modified matrix. So we will swap A and D, so 1, negative 2, and change the signs on B and C. We will be left with 1, negative 1/17. That's our scalar. And then 1, negative 3, negative 5, and negative 2. We'll need to multiply the negative 1/17 through. So we'll have negative 1/17, negative 5, positive 5/17 rather, and positive 3/17, and positive 2/17. We will go ahead and apply our inverse matrix to both sides of the equation. So here's our inverse matrix. I can't write too fast or it does not pick up what I'm writing. Seventeenths. Okay, and then times our next matrix, A, times matrix X equals inverse of A times matrix B. So inverse of A and then B, which is just negative 11 and 19. Okay, now A and the inverse of A gives us the identity matrix. So we really don't need to multiply that because unless you want to be sure you have the correct inverse of A, so it's not a bad idea. And then we'll multiply the inverse of A with B. All right, so we got some fractions here. Thankfully, we're just multiplying these, and they have the same denominator. Okay, so it'll be positive 11/17 plus, and let's see, 3 times 19 gives us 57. So we'll say 57 over 17. And then the next row, negative 55/17 plus 38/17. So the inverse matrix and our variable matrix, matrix X, gives us just the variables. And this works out to be 68/17. And this one works out nicely, negative 17/17. All right, now we will reduce our fractions. So 17 goes to 68 remarkably 4 times evenly, and that reduces to negative 1, the negative 7/17. Okay, so we have our x is equal to 4, and y is equal to negative 1. Don't forget, this is a point on a graph, an ordered pair, so we will write it, our solution, as an ordered pair. So 4, negative 1. And that is our solution that will work for both equations, and hence the system. So the nice thing about matrices is that, let's say this was a system in 3 variables. Well, that would be, solving it this way would actually be a lot easier to do than, let's say, using substitution or elimination. And we could expand to 4 variables and 5 variables. And matrices actually are easier, the more variables you throw in as opposed to doing elimination and substitution. So in 2 variables it is a bit of work. And yes, elimination would probably be easier in this case, but as we expand to more dimensions, more variables, this would make a lot more sense, and now we know how to do that. So anyway, that concludes our foray with matrices, and really this is just the tip of an iceberg, a very large iceberg dealing with matrices. There's an entire course that deals with this called linear algebra, and that's you'll learn that there's a lot to matrices, and it can get into some very, very interesting concepts. But that's all we're going to do for this course. So hopefully you got something out of it. Remember, you can go back and review things that you weren't, 100% picked up on, or you just need to go over, a second or third time. Anyway, I will see you on the flip side. Thanks. Bye.